All right. Well, while we are waiting for the last few to jump on, I will begin the welcome introduction. Thank you, everyone, for joining us today. Allow me to introduce our next two speakers, Adrian Woodhead, Principal Engineer at Expedia, and Christine Mathiesen, Software Engineer, also from Expedia. Just a reminder, if you have questions, please join Adrian and Christine in the Slack community after the session. And with that, let's dive in. Christine and Adrian, take it away.
Thank you very much. So, Subsurface, I'm Adrian, dialing in all the way from London, England, where it's unseasonably hot and sunny. And Christine is about 150 kilometers away from me over in Bath. So yeah, we're going to be talking today about the experiences we've had the last 9 months or so, working on what we call next generation data lake technologies. So we've both been working on the Expedia Group's data lake platform and kind of looking into what could it and should it evolve into in the near future. And Iceberg came up as a table storage format that looks really interesting. So we took a look at it and we did a bunch of work adding Hive read support to Iceberg. So we've imaginatively called that Hiveberg, and that's what we're going to be talking about today. So for those of you who don't know, the Expedia Group covers many different brands and companies, as you can see on the slide. And we provide a wide range of travel solutions from hotels to car rental to flights to vacation rentals and much more. So as I'm sure you can imagine, this means we have a huge variety of different data. We also have a lot of different data. And if we want to get a complete picture over all of this, that's the responsibility of us on the data lake team to manage all of this and make it accessible. So before we dive into Iceberg and Hiveberg, I think it's useful to understand just a bit of the broader context of our data lake journey and how we got to where we are today. So those Expedia Group companies that I just showed you, some of them have been around for a couple of decades, some of them are a bit newer. But the point is we didn't create our current data platform from scratch. It's something that's evolved over quite a long period of time. And we followed a path that I'm sure is similar to many other companies out there. So we started off with what would now be called a traditional data warehouse, with most of the data stored in relational databases, often proprietary. And this was, running on specialized hardware like a mainframe. So then with the rise of Hadoop and big data, we moved a lot of the data sets out into Hadoop to take advantage of the improved scalability that this provided. So we set up a shared on-premise Hadoop cluster, many hundreds of nodes, distributed storage, and we put Hive on top of this to keep track of the table schemas and so on. Because we had such a large SQL footprint from our relational database days, a lot of the data processing and querying that we did in Hadoop was also done using SQL via Hive's query engine. But over time, we ran into problems with not being able to scale out our on-premise cluster to meet peak demand. And we also found that the upgrade path for both the hardware and the software was expensive and painful, as were the operational costs of maintaining all of those machines ourselves. So we decided to move our data platform out into the cloud to take advantage of elasticity, lower operational costs, and the more flexible upgrade paths, and we've created a cloud data lake. So what do we mean by a cloud data lake? So if we start off with what we just consider to be the bare minimum, for us it is the data stored in a distributed file system like S3, and then metadata about this data stored using Hive's Metastore service. So the metadata consists of schemas for every data set, and then these also then point to the physical locations of the data. The Hive Metastore has got wide support for integration with a number of compute and query engines, which we can then use to access the data. So no, we're not limited to just Hive's SQL query interface, but as you can see on this slide, this shows some of what we're using today or plan to use in the future. So these are things like Amazon ZMR, Spark, Presto, yes, Hive's query engine, but then also things like Tableau, Dremio, etc. So this obviously isn't an exhaustive list, but the point to make is that Hive provides us with an interoperability and consistency layer that allows us to be fairly flexible in how we access our data at rest. So there are a number of things we really like in this setup. Most of the foundation is open source, or at the very least, commonly used commodity software. For the most part, it's all being very actively developed. It's evolving constantly, and we've engaged ourselves and contributed a fair amount, which has been great. As I kind of just explained, we've got interoperability with a wide variety of tooling, so we don't get locked into any one data access technology. And then because of our relational database history, we've got a large number of users who are obviously skilled in writing SQL. So being able to keep those skills and reuse them in our cloud data lake is a huge benefit. But at the same time, we're not limited to this. We're also able to use more modern languages and frameworks like Spark, R, etc. And finally, we found all of this to be massively scalable. And we have tens of thousands of data sets, thousands of users, jobs, and systems interacting with the data lake to produce and manipulate multiple petabytes of data. So for the most part, we're happy. We're getting a lot of value out of the flexibility and scalability of this cloud data lake. But like most things in life, there's room for improvement. So I'd like to focus on some of the challenges we face just dealing with the metadata layer that's currently stored in Hive. So we found that in certain situations where, say, you may have a data set that's partitioned by hour and you have a few years worth of data, if for some reason you want to access all of the data for some historical query or you need to reprocess all of the data, this means that the Hive Metastore needs to load up tens or possibly even hundreds of thousands of partitions. And this is not only slow, but it takes up a lot of memory. We have a few users doing this at the same time. It has a noticeable negative impact on our systems. Hive's partitioning scheme tracks data at the folder level. So this means that query planning and execution involves doing file listing operations and potentially reading many files that aren't actually even relevant for the query. So we could look to resolve some of these issues by partitioning the data in a table differently over time. So for example, you could keep hourly partitions for the most recent month's data, which gets accessed the most often. And then you could repartition older, less frequently accessed data into daily or possibly even monthly partitions. Unfortunately, Hive doesn't allow you to evolve your partitioning scheme like this. It's fixed when the data set is created. So you then have to come up with workarounds like having different tables for different partition grains, which isn't ideal. And finally, we have a lot of data processing that restates existing data. So we're not just appending data, but if we want to allow, consistent concurrent read and write access to the data whilst changing it, we effectively have to perform a copy on write of the entire affected partition whenever anything in it changes, even if we're just updating or deleting one row in a partition. So this obviously has negative performance impacts, but there are also operational issues because we have to keep track of what data is in use, when data becomes orphaned and can be scheduled for deletion. And there are also financial storage and processing costs of having to do rewrites at such a coarse grain. But we're not alone in experiencing these issues, and a number of next generation table formats have been designed to deal with precisely these problems. So one of these is Apache Iceberg, which aims to support the storage management and usage of petabyte scale datasets. So Iceberg has a very rich feature set, and there's an entire presentation later on today discussing it in much more detail. So I'm just going to focus on what we thought was the most valuable to us for possible inclusion in our data lake in the future. So the fact that it's an open table format is obviously very important. At our scale, if we're going to commit to storing petabytes of data and storing this going back many years and possibly many years into the future, we want to make sure that this format isn't proprietary in any way whatsoever, and nor is it controlled by a single entity. We'd also like to have the option to contribute to the code base in case we need to add functionality or fix bugs. And what's interesting about Iceberg, it has very good integration with Spark, but it doesn't necessarily require Spark. So they're Java and Python APIs. And what's nice about this is you're not tied to Spark as an execution engine. You can potentially use it from a wide variety of different tools and platforms, and even maybe integrate it into tooling that doesn't exist today, directly from those Java and Python bindings. And one of the key concepts of Iceberg is that it tracks data at the file grain, not the folder grain. So this allows query planning and execution to avoid these potentially costly and eventually consistent file listings. And in turn, this results in improvements in query performance. So Iceberg handles schema evolution very well, but it also has more advanced concepts like being able to evolve the partition layout over time. So coming back to my earlier example, you can repartition data to be at a day or a monthly grain instead of an hourly grain in an existing data set without having to recreate the entire table. It then has a number of advanced features, which Christine is going to touch on shortly. So these are things like time travel, which is especially useful for things like model training and machine learning. There's flexible schema evolution, so you can evolve how you model your data over time, or potentially even have producers and consumers of the data having slightly different views over the same data set. And it then aims for a high level of data correctness and consistency, which we think is crucial when you're making important business decisions on your data. And it allows for concurrent data processing with isolated reads and writes. So I'm now going to hand over to Christina, who's going to talk a little bit more about how Iceberg works under the hood, and then the work we've done to add Hive read support to it.
So as Adrian mentioned, the key idea behind Iceberg is being able to track all of the files in your table over time versus something like Hive, where you're only able to track at the partition folder level. And this is enabled using this concept of snapshots, where every time you make some change to your table, such as a write to add some data, you create a new snapshot. And this creates a really nice linear progression of the changes that have happened to your table over time, and is also the feature that enables time travel. So this here is a diagram of what the Iceberg table format actually is. The table format is made up of multiple layers of different metadata files. And at the top layer, we have the snapshot metadata file. And this essentially contains a complete list of all of the files that exist in your table for that snapshot. It contains information like the table schema, the partition spec, as well as a location of the manifest list. The manifest list is the next layer down and is, as it seems, a file that contains a list of all of the manifest files for that snapshot. For each manifest that it lists, it contains some information about that file. So it'd be things like the range of values that the manifest file spans for the partition column. And this is what Iceberg can use in order to skip reading entire manifest files if the value that you're looking for in your query doesn't exist in that manifest file. And it's the part that allows Iceberg to significantly improve the query planning time. And then the next layer, we have the manifest files, and these contain lists of data files. And for each data file in the list, it also contains some information about that file, such as things like per column, upper and lower bounds, which Iceberg can also use to skip reading individual data files that don't need to be read for a specific query. And then at the bottom layer, we have the physical data files, and they can be written in things like Parquet or C or Avro. So when we were first investigating Iceberg, we took notice of the different query engines that Iceberg supports. And Iceberg comes with really good support for Apache Spark, where you can both read and write Iceberg tables using the DataFrames API. And I believe there's also some work going on to integrate Spark SQL with Iceberg with Spark 3. And the community over at Presto SQL have also written a connector that allows you to read and write Iceberg tables as well, which is really nice. However, when we were investigating Iceberg, there wasn't at the time any integration of Iceberg and Hive. And this is a really key component for us to unlock a shift in our data lake from Hive to Iceberg, as we really need this bridge between the older datasets in Hive and any newer datasets in Iceberg in order to not have a barrier between the two technologies, so we don't have to do a big bang migration of all datasets in one go. And that's what led us to creating this project called Hiveberg, which aims to add read support for Iceberg tables from Hive. So when we first started thinking about Hiveberg, we first engaged with the Iceberg community, reached out to see if anyone was interested in the idea of adding this feature. And we got some good general support for the idea. And we got some pointers and some feedback about how we could go about implementing this. And our initial aim was actually to contribute the project directly to Iceberg, so forking the project and developing in a branch of Iceberg. But what ended up happening was we encountered a large amount of issues with some dependency conflicts between Hive's older dependencies and Iceberg's newer dependencies. So this ended up with us deciding to create Hiveberg as a sort of temporary stopgap project where we could learn and develop in a simple separate project where we weren't being hampered by these dependency conflicts, because it turned out to be a much bigger issue than we initially thought it would be, as it required a change in the dependency resolution plugin that was being used with Gradle. And we got some help from the Iceberg community to fix that issue and get that changed so that we could finally start contributing some of this project back to Iceberg. And then when we first started the project, we decided that we were going to just focus on getting the read path working from Hive, meaning that you can't currently write Iceberg tables via Hive. And this really meant that we could ensure that our existing tooling would be able to access any new Iceberg datasets that we're writing, and allowing for some incremental migration of datasets over from Hive to Iceberg. And it's the part that it would really allow us to make sure that we're not creating any data silos. So how does Hiveberg actually work? The core of Hiveberg is centered around the input format. And this is the bit that essentially integrates Iceberg with Hive's execution framework MapReduce. So it'll take files retrieved from Iceberg tables, split them into manageable chunks for the mappers, and create Iceberg records from those chunks. Then the translation layer is the SERDI bit, which will take Iceberg records and convert them into fields and values that Hive can interpret. Then there's also some translation going on there between Iceberg types and Hive types. And then we have the storage handler, which bundles all the different parts together into one class and makes it easy for a user to pick up the input format and start using it. And it also adds some extension points for us to be able to add some more advanced features to the project. And then the bit that sort of ties everything together is we've been extensively using this project called Hive Runner, which allows us to perform integration style tests by running Hive in memory. So this meant that we could test the input format by running unit tests within our IDE, and it meant we didn't have to go through all the trouble of setting up an external Hadoop cluster to test the input format. This here is a diagram of of how we might want to integrate Hiveberg into our existing data lake. So we have here at the bottom S3 as our storage layer, where both Spark and Presto can read and write Iceberg tables too. But then if we have any users using some of the older technologies, such as Hive and Tableau, they need some of these data sets, they can still access them via the Hive Metastore and Hiveberg. So this means that we're not sectioning off any of our newer data sets from users still using older tools, and everyone has visibility on all the different data sets that they might need to complete the task that they're doing. So these next couple of slides are going to show a bit of example code of how you might be able to use Hiveberg. So the one caveat here is that in order to use Hiveberg, you have to actually create your Iceberg table using some other technology. And here in this example, we're using Spark and the Iceberg Java API. And we're just creating a Spark session, and we're choosing the Iceberg catalog that we want to use to create our table. And in this case, we're just using Hadoop tables. And to create our Iceberg table, we use the catalog to create a table using an Iceberg schema, and then a location where we want our table to exist. And then we're just adding a bit of data to the table by reading in a JSON file and selecting the columns that we want to append to our table. So once you've created your Iceberg table, you can then go to Hive to create your Hiveberg table. To do this, you create a new table and you specify that you want to store it using the Iceberg storage handler. And you give the same location as we just used where your actual Iceberg table exists. That's all you need to do, because then if you run a Hive query like this one here at the bottom, you should see the same results as you'd expect to see if you ran the query directly against your Iceberg table. Once we got the core functionality working, so we could actually read the tables from Hive, we started to have a look at some additional features that we wanted to add so that we could leverage some of the cooler capabilities of Iceberg that would really bring the benefits that we were looking for. And the first main one was this concept of filter pushdown, where you take the filter provided by the user in the where clause of the query and push it down into the Iceberg readers so that they can use that filter to prune away files that don't need to be read for that query. And this is the part that allows Iceberg to significantly speed up the query planning phase, and it's a really big benefit. We then also had a look at adding column projection, which is where you take the columns in the select part of the statement and push them down into the readers so that readers can skip reading certain columns, only read the ones they need to, which also speeds up query execution. And then we also really wanted to add this feature for users to be able to write time travel queries. So allowing a user to specify the snapshot ID or the snapshot that they want to run their query against. This sort of coupled together with adding an extra feature of exposing Iceberg system tables as Hive tables. So this is where users would be able to see the different metadata tables that they have related to their Iceberg table via Hive so they can use some of that information in some of their queries, such as a snapshot ID for a time travel query. So if you wanted to perform a time travel query, you create a Hive table similar to how we did earlier by creating a new table and specifying we wanted to use the Iceberg storage handler in the same location as before. But then when we run a Hive query in the where clause, we specify the snapshot ID we want to run it against. But if you wanted to actually figure out what snapshot IDs you have available for your table, you can create a system table to see that information. To do this, you create a new table and you still specify that you want to use the Iceberg storage handler. You give the same location as before, except you add this extra suffix at the end of #snapshots, which is the bit that specifies to the input format that you want to be loading data from the metadata table versus the original data table. And if you were then to run a select star against this table, you'd see information kind of like this here at the bottom, where each row is a different snapshot that's part of your table, and you'll get information about that snapshot, like the timestamp when it was committed at, as well as the snapshot ID, which is what you can use for the time travel query. So this here is a timeline of how we wanted to contribute the project back to Iceberg. So we started off with some initial PRs with all of the core functionality just to be able to read an Iceberg table. So we got the Surly part merged in first, and then we had a PR open for the initial input format. But we got some feedback from the community and we decided to change our approach. We collaborated with another developer and then got a new version of the input format merged in. And then quite recently, we also got the storage handler part merged in as well. And now that all of the sort of core functionality has been merged into Iceberg, we are looking at opening some more PRs to add the extra functionality like the filter pushdown and the time travel stuff. And once all of the coding stuff has been merged in, we're going to make sure that we add some good documentation on how you'd be able to use the feature. We know documentation is one of the most important bits. So Hiveberg is very much a project that's still in development, and it's still a very fresh project, but it really has the ability to unlock a lot of capability within our data lake. And one of the major key takeaways of this project is that we want to ensure that we have backwards compatibility within our data lake, so that any new data sets created with Iceberg aren't siloed off from from other users using older technology. Adopting Hiveberg would also help us improve existing use cases. So historical queries that look at a lot of historical data would be have significantly improved performance, as well as just general query performance would be better across the board. But also having the additional flexibility of being able to evolve a table schema and a partition spec is a really big benefit. It would also help enable some new use cases, such as version model training, having some data backups, and also being able to roll back our table to older versions as well. Then a key part for us has really been this concept of future proofing. So the fact that the table format is open and that the project is open source means that we can contribute different features back to the project that would really help us to be able to adopt the technology, as like the work we've been doing here with Hiveberg. Now, we really have enjoyed and are excited about all of our contributions making it into Iceberg, and we look forward to all the further PRs on the work we'll be doing in the future. And if anyone's interested in the project, please go have a look. We welcome all feedback and comments. So I believe I could direct you over to the Slack channel. If you have any questions, we'll be around for about an hour. And thank you for listening.
Thank you, Christine and Adrian. We actually do have about 7 minutes left in this session. If you would like to take the first question, we have one here from June. Let's see, June, are you there? Okay, looks like June may have dropped off. How about Alberto?
That's me.
There we are. Hi, Alberto.
Hi. So my question, hi, Adrian. So my question is about what made you decide for Iceberg and not Delta.io or Hoodie or Hive Acid 3? And the second question is about the limitation of the S3 object storage, so that is eventually consistent. So how did you solve the concurrent writes if you have this use case in your setup? Thank you.
Sure, I can take those. So the first one about the choice of technology. So Hive 3 could be interesting, but getting from Hive 2 to Hive 3 is going to be quite a journey. And it has some benefits, but I'm not sure it has as many as some of these sort of next generation table formats that you mentioned. Delta is interesting, and we do use it in parts of Expedia. We use Databricks, and that kind of comes with Delta. So it has lots of good features. Unfortunately, some of its nicer features aren't in the open source version. So that kind of comes back to my thing about whatever we commit to, we would like it to be 100% open source. Hoodie we've looked into also. So kind of want to stress all of this is we're evaluating all three of them at the moment. But what we liked about Iceberg, it just seems to be really well architected, really well thought through. And we've just found the community very, open and engaging. We've had a number of conversations with them, and it just feels like we're really nicely aligned with the vision where they want this table format to go. So I think it lines up nicely with where we could possibly go in the future. For the eventual consistency issue, I think Iceberg is built to solve a lot of those problems. So, it tracks things at the file level. Those manifest files that Christina talked about and the snapshots, each of them has a point in time, all the files that are there. So you don't have to do those list operations. And that's definitely, it's one of the goals of the community is to get around that and to make sure that your data lake is consistent, not eventually consistent for concurrent access.